Howdy, my name is Nicole, and today we're going to talk about chemical kinetics or reaction rates. In particular, we're going to look at how can we change the rate of a reaction and why does it happen? The learning objective that we're using today is essentially we want to be able to identify the conditions that we can use to speed up or slow down a reaction and be able to describe why it happens on the molecular level. This is going to correspond to NGSS Performance Expectation HSPS1 5 or TEKS, which is Texas Essential Knowledge and Skills 10F. So first thing let's do is let's explore what you maybe already know or you have some experiences with. We have sugar going into hot tea, we have glow sticks or glow bracelets, and we have a baking soda volcano. So if you've ever tried to dissolve sugar in tea, you know that the conditions that you dissolve it in change how much you can dissolve and how fast it dissolves. The other thing that might happen with the glow sticks is you might have had somebody tell you at some point in time, hey, if you stick that glow stick in the freezer, it's going to last longer. Or maybe you've made an actual baking soda volcano in your kitchen, or you've at the very least mixed together baking soda and vinegar and watched the bubbles arise. So we're going to do a couple of experiments here. The first thing we're going to look at is how can we dissolve sugar in water and how can we make it go faster? So the constants that we've got, we're going to have 1 cup of water in the same container for each experiment, and we're going to use 1/4 of a teaspoon of sugar. For the first experiment, we're going to look at how does it change the rate if we use warm water versus cold water. And then we're also going to look at what happens if we stir or we don't stir. So from the 4 sets of conditions down at the bottom, warm water and stirring, cool water and stirring, warm water and no stirring, cool water and no stirring. Which one do you think is going to cause the sugar to dissolve the fastest? Once you've decided that, see if you can make a ranking from the slowest to dissolve to the fastest to dissolve for all 4 of the options. Pause the video, write your hypothesis down, and play it again when you're done. Okay, so on this screen, what we're going to see is we're actually going to see all 4 videos. We're going to see all 4 trials of this experiment and see what happens. They don't all go in at quite the same time, but they're relatively close. So from left to right, we have the warm water being stirred, the cool water being stirred, the warm water not being stirred, and the cool water not being stirred. As you can see, in the time that it took me to talk about this, the warm water being stirred has already completely dissolved. The cool water being stirred is not far behind. And then the warm water, I don't know if you saw it, but at the beginning it was all kind of cloudy and you could actually see the particles moving around in there, almost like a little bit of a current. And then the cool water one is just kind of stuck. It's a little bit dissolved. It's going away really, really slowly if you watch it, but it doesn't really appear to be going away very quickly. Okay, so now if we do a similar experiment where we react the baking soda and vinegar, so just like the baking soda volcano, our constants again are going to be the amounts of our reactants, so 2 teaspoons of vinegar and 1 teaspoon or half a teaspoon of baking soda, and then the same container. For the first experiment, we're going to look at the same thing over again. We're going to look at the warm vinegar versus the cool vinegar. And then for the second experiment, we're going to change the concentration. We have a set where we have 5% vinegar, which is the vinegar that you pour straight out of the bottle. And then where I diluted it, where I had 1 part vinegar to 3 parts water. So it made it 1/4 as concentrated. Okay, so here is our 4 possible situations. I would like for you to take a look at these options and decide which one you think is going to be the slowest to react. Okay, so our first experiment, looking at the warm vinegar versus the cool vinegar. Let's see what happens. Okay, in the warm vinegar, we see that the bubbling up happens much more quickly and then settles down again. And then in the cool vinegar, it bubbles up to almost the same height, but the bubbles kind of appear smaller, and you also end up with the reaction going on a little bit longer. Now, the second experiment is the 5% vinegar versus the 1.25% vinegar, so concentrated versus dilute. As we add the 2 bits of vinegar, you can see that the 5% vinegar solution, the bubbles get much higher, much more quickly, and then start to dissipate. Whereas in the 1.25% vinegar, it bubbles up some, but it doesn't really even look like it gets all of the baking soda to starch to react. Okay, so why do these things happen? We've looked at heating the solution, we've looked at stirring the solution, and we've looked at the concentration of the solution. And now we're going to look at why all of those things happen. We're going to use something called collision theory to help us figure this out. Collision theory pretty much just says that a reaction rate depends on how often molecules or particles hit each other and how effectively they hit each other. What you end up with is with collision theory is that when you have molecules collide, the more collisions that you have that are effective, we'll talk about that in a second, the more you speed up the reaction rate. So effective collisions have to have 2 things in order for them to work. The first one is they have to have the correct orientation, meaning that they have to hit each other from the right angle or they won't actually interact. The second thing is that they have to have enough energy. If they only have the correct orientation or they only have the correct energy, the reaction won't happen. Another way to think about it is if you look at the reaction energy diagram here, we have the energy of the reactants, the energy of the products, and then this little part right here is the activation energy. The reactants have to have enough energy to overcome this activation energy before they can react. So in order to get an effective collision, you have to have both the correct orientation and a sufficient amount of energy. In this case, the energy is denoted by the length of the arrows. So let's take a look at some examples of this. So this first example, and I want to say thank you to University of Colorado Boulder for their amazing PhET simulations. This example shows the atoms hitting each other in the correct orientation, but they don't have enough energy to overcome the activation energy barrier. So a low energy collision, even if it's at the right angle, does not make a reaction. In this example, we have a high energy reaction, which I can show you by, you can see the little thermometer there. Okay, the high energy reaction, so there should be sufficient energy, but because the 2 particles hit each other at a different angle, they were not able to react. And then finally, if we have a particle with sufficient energy and the correct direction, you can see that the reaction occurs here. We switched from the purple and gray to the yellow and purple, and that's an example of the reaction happening. So a high energy particle with the correct angle is the only way to make an effective collision. So we looked at some things that we want to create faster rates by creating more effective collisions. That's really what it kind of comes down to. So when you stir a solution or you stir a reaction, we are artificially making the molecules collide more often. Sometimes we could speed up the particles a little bit, but by stirring it, we're moving the components around more than they would on their own. And so we're creating more collisions. And just by creating more collisions, we can actually get more effective collisions. The second thing we can do is heat the reaction. When we heat the reaction, this causes a change in the kinetic energy of the system. So if you have something moving really slowly, then it has low kinetic energy. If you have something moving fast, you heat it up, it's got lots of kinetic energy and it goes really, really fast. So 2 things happen there. When the kinetic energy increases and the particles go faster, you end up with one, more collisions happening, period, because they're just moving around faster and bumping into each other more. And then two, more of the particles have enough energy to get over that activation energy curve. Okay, so let's take a look and see what we have here. We have a few particles. I'm going to raise the temperature. And once I raise the temperature, I'm able to get a reaction to happen. So I end up with, at low temperatures, there are fewer effective collisions, and at higher temperatures, there are more effective collisions, which means a faster rate. Okay, so this is just kind of a side-by-side example. In this one, you can see that we have just one particle that has been able to react, and it has a lower temperature, whereas this one has a higher temperature or higher energy, and more particles have been able to react because they're moving faster and they hit each other more, and they have more overall kinetic energy. The third way we can change the reaction rate is by increasing the concentration. If we increase the concentration, we know that the reaction is going to happen faster. If we try to connect this back to our collision theory, this goes back again to more collisions make a faster rate. So in the case of concentration, what we have is we just plain have more particles. If you wanted to think about it in a kind of a silly way, you could think about it as a room full of kindergartners. If you have 5 kindergartners in the gym and they're all playing soccer or tag or something like that, there's a lot of space for them to run around in before they can bump into each other or bump into the walls. But if we take that same gym and we put, I don't know, maybe 50 or 100 kindergartners in it, pretty soon you're going to have somebody that gets hurt because they're going to bump into somebody else, or they're going to bump into the wall, or they're going to trip over something. There's just more kids in there, and more kids means more interactions. Let's take a look at what that looks like on the particle model. So here's an example of a low concentration system. I did have to raise the energy a little bit because it was a little bit low there to reach a point where it would react. But at low concentrations, there are fewer collisions simply because there are fewer particles. At high concentrations, you end up with more particles, therefore more collisions, and of course, a faster reaction rate. Do have to warm this one up again a little bit. Okay, as you can see, as I heat it up, the particles actually do move faster. And then as time goes on, there are more particles that are able to react. Okay, here's again a still of the remaining components, the low concentration versus the high concentration. We're assuming that they are at the same temperature. Okay, here's our last thing. And I couldn't show you this one earlier because it's not safe to do at home. What we're looking at here is how does surface area affect the ability of a reaction to occur? So what this gentleman from Carleton University chemistry show has in his hand is called lycopodium powder. It is a pretty interesting substance. It is flammable, but as you can see, he puts it in his hand, he lights the match and touches the match to it, and all we see is a little bit of, like scorching. So the reaction that's happening there is not happening very quickly. Let's compare that with what happens in a high surface area experiment involving lycopodium powder. So in this case, he's put the powder into a straw and he's blown it out so that it spreads out and increases the surface area. You can see in that video pretty easily that when he increased that surface area, that he was able to explosively increase the reaction rate. It's pretty fun to see. Make sure you do not try this at home. Okay, so collision theory, because that's the whole point here. Collision theory with surface area relates to just how many pieces can hit each other at the same time. If you have a big block of material and you have water molecules coming at it from all around, you end up with only the outside edges can interact with the water. So that slows down the reaction rate. Whereas if you take that block and you break it into a whole bunch of tiny little pieces, and water can hit each one of those little pieces from the side, or any side, then that gives you a lot more places for effective collisions to happen. Therefore, you end up with a higher reaction rate. Okay, so let's do a little bit of review. The first thing we want to look at is which of these things work to speed up a chemical reaction. And again, they're all going to be based on increasing the number of effective collisions. So you can either write down each of the pairs or just write down the correct answer for which one in each pair of conditions will increase or speed up a reaction. Pause the video and do that, and then start it back up when you're ready. Okay, between warmer and cooler temperatures, warmer temperatures means more kinetic energy, means faster movement, means more effective collisions. Higher concentrations mean more particles hitting each other, therefore more collisions, and substantially or statistically, more of them will be effective. Stirring provides a mechanical way of making the molecules hit each other and increasing the number of collisions. And then having small pieces or high surface area also increases the reaction rate. Okay, so we have 4 of these. Each of these statements is false, and some of them are kind of tricky. You got to really read the wording. What I want you to do is to change the word in each of these sentences that makes it a false sentence into a true sentence. There's only one word that needs to be changed. So take a moment to review each of these, pause the video, decide what word needs to be changed in each case. Start the video back up when you're ready. Okay, in the first example, the glow stick getting brighter indicates that you have a faster chemical reaction. If you want a faster chemical reaction, then you have to have either stirring, more kinetic energy, so hotter temperature, or higher concentration. Since that glow stick is sealed, pretty much the only thing you can do to it is raise the temperature. So the glow stick gets brighter when we put it in hot water because the particles are moving faster, giving you more collisions. The second example is a really kind of scary but true real world example. It's not so much anymore because we don't have so much farming in America anymore. But if you have a grain silo, there's always flour and all these little tiny particles all throughout the air, much like that lycopodium powder that we saw where the whole fireball exploded. If you have tiny flour particles mixed all throughout the air, if you got just the tiniest little spark in there and it was enough to start one little flour particle on fire, that could spread through the whole grain silo really, really fast. So what we did in this one is the grain silo with the flour particles is an explosion risk because of the increase in surface area rather than the big mound of flour. All right, we got 2 more questions. Take a moment to read these, decide which one word needs to be fixed, pause your video, and then when you're ready to check, start it back up. All right, so these 2, we had temperature already, and then we had surface area. So these 2 involve concentration and stirring. So if we want to slowly, that's the key word there, slowly etch a piece of metal, we want to use a dilute acid because we actually want to slow down the reaction. So if we want to use a dilute acid, that's less concentration, which means less particles, which means fewer collisions. In the stirring example, we stir, or when we stir, we mechanically increase the reaction rate by making more of the particles bump into each other because we're making them move around more. The last thing I wanted to do is to actually display the true standards, the NGSS standard and the TEKS, and to provide a couple of acknowledgments for resources that I used to create this presentation. Here is the NGSS performance expectation related to reaction rates in collision theory. Okay, and here is the Texas Essential Knowledge and Skills related to kinetics or reaction rates. And finally, I'd like to say thank you to the University of Colorado at Boulder for all of their amazing PhET simulations, which allow us to view things that we could not otherwise see. In addition to the Carleton University Chemistry Magic Show and their YouTube video describing and showing the effects of surface area on reaction rate in a really fun way. All of the other videos or images are either made by me or were taken through a Google search through a reuse with modification copyright allowance. I appreciate your time, and I hope you learned a little bit about reaction rates today.